Hi, welcome to the video presentation for VarCLR. I'm Qibin Chen, and I'm glad to share our work on variable semantic representation pre-training via contrastive learning with my co-authors Jeremy, Ed, Graham, Bogdan, and Claire. We propose a novel framework based on contrastive learning that provides better variable name understanding and can serve as a drop-in replacement to existing approaches like Word2Vec or CodeBird, and potentially benefit a wide range of downstream tasks involving variable names. First, variable names are important parts of software engineering. Even though they don't directly affect the execution of programs, developers still spend some time writing good variable names to help other programmers to understand the code semantics. So let's have a brief look at this simple example from LeetCode. This is a one-liner solution to a dynamic programming problem, and without good variable names, you can see it's almost impossible to figure out the meaning of this code. And this study back in 2006 found that in terms of helping developers understand the meaning of the code, full-word variables are slightly more helpful than their abbreviations and much more helpful than single-character variable names. But variable names can become much more useful than simply providing information to human developers. And nowadays, humans are not the only programmers. And for tools like Copilot, recent studies have shown that these transformer-based models are extremely dependent on textual cues, including variable names, function names, or comments, to understand the program. In the software engineering community, there are also a wide range of applications that can potentially benefit from a good understanding of variable names, like inferring the type of variable from the name, or suggest similar or better variable names. Other researchers have tried to use variable names to match APIs between different languages, and even automatically detect bugs based on variable names and function argument names. Although these tasks appear to be very different from each other, they share one underlying problem, which is variable representation. The quality of variable representations can reflect the ability of the model in understanding the meanings of the variables. It can directly affect the performance of downstream tasks that are relying on variable names. Because variable names are so important for so many tasks relying on variable names, or just use variable names in their analysis, we want to explore what properties make good variable representations, and is it possible to improve them in a unified way so that all of these tasks can benefit from a better variable representation. There are 5 properties that we currently believe are important properties of variable representations. They are character similarity, open vocabulary, subword importance and order, and most importantly, relatedness and similarity. The first property is character similarity. So variables that look similar to each other should have similar representations. For example, the difference between the misspelled main and the main is really small, and also the single character difference between British English and American English, like 2 versions of center. This sounds very simple, but it does not always work, and unfortunately, it can even be misleading. Consider the following examples. Length and size are synonyms, and they are often used to represent the length of the array, vector, or dictionary. However, they almost share none of the characters. The same applies to mean and average. On the other hand, minimum and maximum are antonyms, but the Levenshtein's distance between minimum and maximum is equal to the distance between minimum and minimal. The second important property is open vocabulary. In natural languages like English, people use a fixed set of words to express their meanings, and in code, the syntax and grammar of a language can be fixed for years. But for variable names, developers are creating new ones all the time. They can become quite long in big projects. We found that you can't always split them into words by camel case or snake case, because there are arbitrary abbreviations and contractions people invented. It is important for the variable representation to be robust to these changes. We also recommend that we should treat variables as sentences instead of words, as an analogy to natural languages. This brings to our next property, which is subword importance and order. Different components in a variable name, which we call subwords, can contribute differently to the overall meaning of this variable. This importance can even change dynamically. For example, when comparing xmin to xmax, we want min and max to be more important. But when comparing xmin to ymin, we then want xy to be more important. And also the order of these subcomponents can affect meaning, like index to word or word to index. These problems suggest that we might need to consider more sophisticated methods than simply taking the average of the subwords as a representation of the whole variable. After discussing some of the technical challenges of variable representations, let's dive into the fundamentals and discuss what should be the meaning of a variable and how to make machines understand the meanings of variables like human developers do. Let's have a look at these examples, I and j and length and size again. So from the property we have discussed so far, like the character similarity, they are not similar and they don't have the similar meanings. However, as human developers, we know they often have similar meanings from the first sight of them. So where does our knowledge about the meaning of these variables come from? They come from coding conventions, or in other words, the code we have seen so far in our programming life. This idea that the meaning of a variable comes from its context instead of the characters in the word itself is called the distributional hypothesis. It is proposed in 1954 and later popularized as a word is characterized by the company it keeps in 1957. It is very likely that you have heard of this before and even used methods like word2vec, which are based on these distributional hypotheses. But it is also very likely that you have been using them as a black box method or a drop-in replacement to some heuristic methods, because this is how they are supposed to work. But how effective are they capturing the information required by the application, and is the model's understanding of variable meanings consistent with your understanding or other developers' understanding? So this work called IDBench at last year's ICSE proposed to evaluate the state-of-the-art machine learning-based methods in terms of how they align with human developers' judgments of variable meanings. And relatedness is one of their benchmarks. So they ask human developers to rate how related are these identifiers. In this example, it's radians and angle. So they are related. As another example, I and j are also related. And it is also worth noting that some opposite operators like add and remove, set and get are also considered related because they kind of pair in the similar context. And they found these approaches like word2vec and fast text are actually quite effective at representing relatedness. However, relatedness is not the full story of meaning, and it has significant limitations. Let's have a look at the following example from Google's word2vec embeddings. Here, we want to find the closest word or the most similar words to the word minimum in the embedding space. The results are displayed in yellow text in the bottom right part of this page. So as you can see, the top one result is maximum, which is the exact opposite of minimum, and the second result is wage. So perhaps this is because there are lots of articles talking about minimum wage, and by the definition from distributional hypothesis, they are located in a similar context, so they end up with similar representations. However, the ideal result we want, perhaps in most cases, is minimal or mean, which has the similar meaning to the word minimum. So here is another very important property of variable representation, which is similarity. We want to intentionally distinguish similarity from relatedness. So here by similarity, we mean two variables are similar to each other if they are substitutable or interchangeable to each other. In the following example, min text and the minimum text, they are related and they are similar. On the other hand, min text and max text, they are related, but they are not dissimilar. It is not okay to rename min text to max text without modifying the other part of the code or the meaning of the code. We can already see here that similarity is very important. Say you are in an application like refactoring or suggesting similar variable names, you want to suggest these names based on similarity instead of relatedness. Like you don't want to suggest people to rename their min text to max text. However, as you might have guessed, even the state-of-the-art method evaluated in the IDBench paper does not handle similarity very well. And in this example, we have two pairs, padding top and padding right, min text and max text. And even the best performing model from IDBench think they are similar and they are kind of substitutable to each other, while humans give this score of 0.07 or 0.05 to indicate that they are not similar at all. So why are they not aligning with humans or even actively aligning with human ratings? We find that it's not because the models they use are not strong enough or they are not using enough data. So we have seen even the models from Google have a similar problem. And the real cause of this is the distributional hypothesis, which is the underlying assumption these models are based on. So it's actually the best you can learn from this data, and related variables instead of actually similar variables will end up with close representations no matter how much data you use. So now we have discussed what properties make good variable representations, and especially the difference between relatedness and similarity. And we have seen there's a lot of room for improvement for these current methods to capture relatedness. So we propose VarCLR, which tries to improve these properties, especially the similarity. Our work is built on these state-of-the-art approaches like Word2Vec, fastText, and the more recent Subword. And our VarCLR models are intended to serve as drop-in replacement to these existing approaches. So existing applications using these methods as their variable representation can directly benefit from VarCLR training. So how did we improve this similarity? Our main approach is based on the contrastive learning framework. Contrastive learning has gained popularity in the machine learning community because they can learn better representations for text, images, and maybe other modalities. Here is a motivating example for contrastive learning. Suppose now we have 4 related sentences talking about the score of accepted ICSE papers. The sentence on the left and the first sentence on the right are both saying that the minimum score of an accepted ICSE paper is 3. So as you can see, they are talking about the same thing, they are similar and they are interchangeable. On the other hand, the remaining 2 sentences on the right have different meanings. So with methods based on the distributional hypothesis, all 4 sentences here might end up with very close representations. Because remember, we showed that maximum and minimum have very close representations from Word2Vec embeddings. But what we want is to make the representations of the left 2 samples to be close to each other, while making the representations of the right samples to be relatively far apart from the left ones. So contrastive learning can help us solve this problem, and an intuitive way to explain contrastive learning is as follows. Given similar or dissimilar pairs, contrastive learning learns an embedding space where similar sample pairs are close to each other while dissimilar ones are far apart. Note how this is more flexible compared to methods relying on the distributional hypothesis like Word2Vec. Here we can define similar pairs and they don't have to come from the similar context, and the algorithm does not make any assumption on where the similar pairs come from. So now let's try to put the previous examples into the framework of contrastive learning. The first sentence is called the anchor, and the similar sentence in the blue color is called the positive. And the next 2 sentences in the red color with different meanings are called negatives, so they are considered as dissimilar in this example. And they are encoded by this encoder, which is could be an embedding layer or can be more capable network like transformer layers. They will be encoded into vectors as indicated by these little squares. And the sphere on the right represents the whole embedding space. And contrastive learning will try to pull close the representation or the embedding between the anchor and the positive, while trying to push apart the embedding between the anchor and the negatives. And this is what we want in this application, because we want the anchor and the positive have a higher similarity score, so that maybe we want to paraphrase anchor, then we should suggest positive instead of suggesting this opposite meaning negatives. And another detail here is that for each anchor sample, we only care the distance between anchor and positive and the anchor and negatives. So as you might have noticed there, the negatives don't have to be similar to each other. So there is no arrow between the negatives or between the positive and the negatives. So these positive and negative pairs are great. When used properly, they can help guide the model to learn more accurate representations compared to learning with the distributional hypothesis. And there are already lots of ways to create positive pairs in the machine learning community. For images, you can apply multiple augmentations like random crop, resize, clip. And for text, you can randomly drop out a word in a sentence. And you can also use labels produced by humans, saying maybe 2 sentences are entailment to each other or they are contradiction to each other, corresponding to the positive and negative pairs. You can even find positive pairs across modalities. Say you can use an image as the anchor and the corresponding caption to be its positive. This is actually the core idea in OpenAI Clip. They might scale to more data and then larger transformers, but their underlying idea is very similar. Now back to variable names. we collected and released this dataset called GitHubRenames. It consists of variable pairs that come from before and after the renaming activities by GitHub developers. We collected more than 60,000 pairs from more than 500 high-star C# projects. And we also only select the edits where the only change is the variable name, ensuring that the other parts of the code are not changed. So the functionality of the variable after the renaming is not changed, and they should be interchangeable to each other. So here is a glance into our GitHubRenames dataset. In this example, there are 3 pairs of variables that will be treated as the positive pairs. And as you can see here, the last pair is mean data points in leaves and minimum example count per leaf. So now let's see how can we use these pairs mined from GitHub and use contrastive learning to improve variable representations. This is the overview of our VarCLR approach, and we will walk through this briefly step by step, but for more detailed discussion, please refer to our paper. First, we use the variable pairs collected in the GitHubRenames dataset as the positives in contrastive learning. And now, suppose we have 3 positive pairs. For each variable in a pair, we use the variables in the other 2 pairs as negatives. The intuition behind this is that it's very unlikely that 2 randomly sampled variables will have the same meaning. And there is some chance that 2 randomly sampled ones are actually similar, but because that chance is so small, it does not affect the effectiveness of the overall approach. And this is usually referred to as in-batch negatives. And then after we have these variables and the corresponding pairs, we use encoders to encode them into vectors. And there are a lot of options for encoders, such as simple ones like word2vec and more capable ones like Subword. Remember earlier in this talk we discussed some other desired properties of variable representations, and in our paper we have discussion on how these different choices of encoders capture these different desired properties. And then finally, we use the info and CE contrastive objective to calculate the contrastive loss based on these vectors. And again, for more details, please refer to our paper. Now let's have a look at how we evaluate VarCLR and compare it against previously state-of-the-art methods. We use IDBench as our main evaluation benchmark, including 2 tasks, Relatedness and Similarity. There are also 3 variants for this benchmark. They are small, medium, and large. The small one has the least number of samples, but the highest quality, which is the agreement between the annotators. And the large one has the most number of samples, but the least agreement between annotators. For metric, we use Spearman's rank correlation between the model's cosine similarity prediction and the human ratings of this similarity or relatedness. For baselines, we use heuristic methods like Levenstein distance, and also machine learning ones like word2vec, fasttext, and path-based methods introduced in IDBench. And for VarCLR models, we try to use different types of encoders, including word2vec, LSTM, and Subword. And remember, our VarCLR method is not bound to any of these encoders, and we can improve all of their representations in general. So we comprehensively evaluate all of these combinations and report all the results in our paper. But here, let's first have a look at the most important results from our experiments. First, our best performing model improves the previous state-of-the-art approach from 0.73 to 0.80 on IDBench large. This improvement might not seem a huge leap, but remember, our goal is to improve similarity, and the fact that improving similarity does not harm relatedness and even improves relatedness further is actually very encouraging. And second, let's see how much improvement VarCLR can achieve on similarity. We improved the previous best performing method from 0.35 to 0.53, which is a very significant improvement. And for more details about our results, please scan this QR code below or just refer to our paper. We also did some ablation study to find out how much each component is contributing to the final improvement. And we found out the improvements come from both the contrastive training and the more advanced choices of encoders like Subword. In this figure, the y-axis represents Spearman's rank correlation, which is the score of this task, and the x-axis represents the percentage of training data we use for contrastive learning. And for the 3 lines, the blue one represents averaging the word2vec embeddings, and the orange one represents using LSTMs on top of the word2vec embeddings. And finally, the green one represents using Subword to encode variables. And as you can see here, at 0% of training data, which means we don't run any contrastive learning and use their off-the-shelf weights pre-trained by these previous works. And their performance is not very good, especially for CodeBird, because it was trained to encode the whole code snippet. And when directly applying it to encode variables, which are not complete code snippets, it fails to generalize to perform well. But with the help of contrastive learning, all three models can be improved, and the improvements become larger with more amounts of contrastive training data. And interestingly, the CodeBird model finally outperforms the other two methods because it is more powerful and can capture more desired properties that we discussed before, such as subword importance. And with proper training with our objective, it can perform much better compared to the other baselines. And in VarCLR, we also evaluate the learned representation on two other tasks. They are similarity search and spelling error correction. And for the experimental results and the discussion, please refer to our paper. And finally, we want to present that VarCLR is very easy to use on GitHub. You can scan this QR code on the right to visit our GitHub repository and find detailed README to guide you how to use our off-the-shelf pre-trained VarCLR models. And remember, even if this is a deep learning project, when you are applying VarCLR to applications, there is no GPU required. And in the end, this is a brief summary of this video presentation. And we will be very happy to discuss the limitations and maybe future work directions and hear your feedback at the ICSE paper. So please come to our paper session and welcome to our poster too. Thank you for your attention.